Hello everyone, this is Syed Afriq from the section C of AML. Today my topic is AquaPredict AI from the subject of DBMS, that is Database Management Systems. So I want to start with the introduction to my topic, that is AquaPredict AI. So here the AquaPredict AI is a smart system that forecasts water quality using real-time sensor data and historical records stored in a robust data. It supports environmental monitoring by predicting contamination risks in rivers, lakes, and the reservoirs using machine learning models. The system integrates IoT sensors, cloud databases, and AI algorithms to deliver timely alerts for unsafe water conditions. Designed for manipulators, environmental agencies, and researchers, it enhances the decision making in water resource management. This project demonstrates how database systems serve as a backbone for scalability, reliability, AI-driven environment applications. The next one is role of database in AI systems. Databases store structured water quality data such as pH, dissolved oxygen, turbidity, and temperature for multiple sensor locations. They ensure data consistency, integrity, and availability of training and inference in machine learning pipelines. Efficient indexing and query operations allow fast retrieval of time series data needed for model retraining and real-time predictions. ACID properties guarantee reliable transitions when logging sensors, readings, or updating prediction results. And the modern systems use hybrid storage relations for metadata and NoSQL or the time series databases for high frequency sensor streams. And the next one is data sources and collection architecture. AquaPredict collects data from IoT sensors deployed across water bodies, transmitting readings every 5 to 15 minutes via LoRaWAN or cellular networks. Each sensor node records parameters like temperature, conductivity, nitrate levels, and chlorine concentrations with timestamps and GPS coordination. Data is ingested into a staging area using message queues like Kafka to handle bursts during storms or equipment spikes. Metadata about sensors, health, calibrations, dates, and locations are stored in the relational database for maintenance tracking. Edge preposition filters out outliers and missing values before transmissions, reduce bandwidth and improve data quality. The next one is database schema designed for water quality data. The core schema includes tables, sensors, sensor ID, location type, readings, timestamp, sensor ID, pH due turbidity, and alerts, alert ID, severity, timestamp. Time series data is parsed by date and sensor ID to optimize query performance and support efficient range scans. Foreign keys enforce referential integrity between readings and sensor metadata, ensuring traceability and auditability. Foreign keys enforce referential integrity between readings and sensor metadata, ensuring traceability and auditability. So views are created to aggregate daily averages of the log anomalies for reporting dashboards using environmental offices. Normalization reduces redundancy while materialized view improve performance for the frequently accessed summary statistics. Data processing and feature engineering. Raw sensors data undergoes cleaning. Missing values are imputed using linear interpolation and outliers are removed via Z-score filtering. Temporal features like rolling average is the 24-hour mean pH and the rate of chance metrics and the compute to the capture trends. Special features include proximity to industrial zones or upstream pollution sources derived from GIS integration. Categorical variables like weather conditions or seasons are one hot encode for model compatibility. Feature stores catch engineered features to ensure consistency between training and inference pipelines. The machine learning pipelines overview. The pipelines include data extraction from the database, feature transformation, model training, validation, and deployment. Models are trained offline on historical data and updated weekly using influential learning techniques. Predictions are generated in near real time by querying the latest sensor data and applying the trained model. Model performance is logged in the database, enabling comparison across versions and drift detection over time. The system supports multiple algorithms, random forest for interpretability, and LSTM networks for temporal pattern recognition. And the model selection and training strategy, random forest is used for its robustness to noise and ability to handle mixed data types without extension scaling. LSTM networks capture long-term dependencies in the time series data, such as gradual pollution, billing after rainfall. Models are evaluated using metrics like RMSE for regression tasks and F1 score for binary qualification of safe or unsafe water. Cross-validation is performed across different time windows to avoid data leakages and ensure temporal generalizations. Hyperparameter tuning is automated using grid search with results stored in the database for reproducibility. The real-time inference and alternating systems. Incomplete sensors data triggers inference every 10 minute uses a lightweight model deploy via RST APIs. Predictions include risk scores for contaminations events such as algal blooms or the chemical spills with confidence intervals. If the risk exceeds a threshold, the system logs an alert in the database and notifies stakeholders via email or the SMS. Alerts are enriched with context, recent weather, upstream activity, and historical patterns for better interpretation. A dashboard visualizes predictions, sensor status, and alert history, pulling data directly from the database. In the scalability and the performance optimization, database shading by geographical region allows historical horizontal scaling as more sensors and deploy across districts. Coaching frequently accessed data example recent readings. In Redis reduction load on the primary database, batch processing handles model retraining overnight while streaming pipelines manage real-time inference. Indexing on timestamp and sensor ID ensures subsequent query response for time range lookups. Connection, pooling, and real replicas improve through output during peak reporting audit periods. Security and data governance. Role-based access control ensures only authorized personnel can view raw data or modify model parameters. All data transmissions are encrypted using TLS and sensitive fields are masked in the logs and reports. Audit trails track who accessed or modified data, supporting compliance with environmental data regulations. Data retention policies automatically achieve old record to cold storage after 2 years to manage costs. Regular backups and disaster recovery plans protect against data loss due to hardware failure or cyber attacks. Case study predicting algal blooms in Lake Hydra. AquaPredict was deployed at Lake Hydra where nutrient runoff from farms often trigger toxic algal blooms. Historical data from 50 sensors over 3 years was used to train an LSTM model predicting bloom likelihood 48 hours in advance. The model achieved 89% of accuracy by correlating phosphate levels, temperature, and sunlight duration with past bloom events. Early warnings allowed authorities to restrict water usage and deploy aeration systems, reducing public health risks. And the performance metrics and sensor logs were continuously stored in the database post-event analysis and model refinement. The challenges and lessons learned. Sensor drift and calibration issues introduced noise requiring robust processing and periodic recalibration protocols. Network outages cached data gaps, mitigating by local buffering at edge devices and retry mechanisms. Model performance degraded in winter due to frozen sensors, highlighting the need for environmental adaptability. Database schema involving required careful migration planning to avoid downtime during system updates. Collaborations between data engineers, domain experts, and ML developers are essential for system reliability and usability. Future enhancements and research directions. Integrating satellites imagery to detect surface changes and validate sensor-based predictions at scale. Using graph databases to model water flow networks and simulate contamination spread across connected bodies. Implementing federation learning to train across multiple lakes without sharing the raw data, preserving privacy. Adding explainable AI components to help officials understand why a prediction was made, increase or the trust. Exploring blockchain of tamper-proof logging for environmental data to in regulating the reporting scenarios. Thank you for giving this